Sometimes, the most terrifying disasters do not begin with an explosion. They begin with a calculation that seemed correct, a material that seemed safe, a warning sign that looked too small to matter. From bridges that twisted apart in the wind, to tunnels designed so people can escape fire in minutes, to spacecraft destroyed by a piece of foam, these are the engineering disasters and defenses that changed how the world builds. Stay until number 1, because the final case proves that in engineering, even a small object moving at high speed can become a death sentence. Before we begin, tell us in the comments which one you think changed engineering the most. This bridge did not collapse because it was old. It collapsed because it moved too beautifully. Imagine a long, narrow suspension bridge stretching across the water in Washington state. At first, it sways gently in the wind. Then the movement grows stronger. The roadway begins to ripple like a ribbon. Cars are trapped on a bridge that looks almost alive. Then the deck twists, steel groans, the bridge tears itself apart. The Tacoma Narrows Bridge opened in 1940 and quickly became famous for its dramatic movement in the wind. People even called it Galloping Gertie. Engineers had built a slim, elegant bridge, but the design was vulnerable to powerful aerodynamic forces. The disaster became one of the most important lessons in bridge engineering. It showed that structures do not only need to be strong against weight, they must also survive motion, vibration, and wind behavior. The bridge collapsed only months after opening. What looked like flexible movement was actually a warning. The wind was feeding energy into the structure, and the bridge could not dampen that motion fast enough. It was not simply blown over. It was shaken into failure. The Tacoma Narrows collapse changed how engineers studied bridges. Wind tunnel testing, aerodynamic design, and structural damping became far more important. Every modern long-span bridge carries the memory of this failure. It taught engineers a brutal truth: elegance without stability can become a trap. But if the Tacoma Narrows Bridge showed how wind can destroy a structure, the next one shows how engineers design escape routes before disaster even begins. From a bridge that failed in the wind, we move underground to one of Europe's most ambitious tunnel safety designs. The most important part of a tunnel is not always how cars and trains enter it. It is how people escape when something goes wrong. Picture a long underwater tunnel stretching beneath the sea between Denmark and Germany. Inside, cars and trains move through separate tubes. But hidden between those tubes is the real survival system: emergency doors, escape routes, ventilation controls, and rescue access designed for the worst moment possible. A fire in a tunnel is not like a fire in the open air. Smoke has nowhere easy to go. People have seconds to make good decisions. Emergency services can also use an unblocked tube to reach the incident faster. This is engineering built around human panic, not just concrete and machinery. The tunnel also has a powerful ventilation system that can control airflow direction. In normal conditions, traffic creates a piston effect, pushing air through the tunnel. But during an incident, the ventilation system can be deployed instantly to support the safest smoke direction. In a tunnel fire, smoke can kill before flames do. This is what modern disaster defense looks like. Engineers are not only asking, can we build it? They are asking, when something fails, how do people survive? That shift changed mega-project design around the world. A tunnel is no longer just a passage. It is a controlled emergency environment. The Vajont Dam itself did not completely fail. That is what makes this disaster even more chilling. High in the Italian Alps, a massive concrete dam stands between steep mountain walls. Behind it sits a reservoir. Above it, a mountain slope looms quietly, holding a hidden danger that engineers did not fully stop in time. Then, one night, part of the mountain collapses into the reservoir. The water rises like a weapon. A wave surges over the dam and rushes into the valley below. The Vajont Dam disaster happened in 1963. A huge landslide fell into the reservoir, displacing water with incredible force. The dam remained standing, but the wave overtopped it and destroyed towns below. This disaster changed how engineers think about dams. It proved that a dam is not just a wall, it is part of an entire landscape. The terrifying detail is that the dam's concrete structure survived. The failure was not simply the dam breaking apart. The disaster came from the environment around it. That makes Vajont a warning against narrow thinking. A structure can be technically strong and still be deadly if the system around it is unstable. Entire communities were destroyed. The disaster forced engineers, geologists, and governments to treat landslide risk as a central part of reservoir planning. Vajont became a lesson written in grief. Nature does not care how strong your wall is if you misunderstand the mountain beside it. This was not only an oil spill. It was a failure of pressure, equipment, decisions, and emergency defense. Picture an offshore drilling rig floating in the dark waters of the Gulf of Mexico. Far below, a well reaches deep into the earth. On the surface, workers move through steel decks, pipes, control rooms, and machinery. Then pressure surges. Gas rises, alarms sound, fire erupts across the rig. The ocean itself becomes part of the disaster. The Deepwater Horizon disaster happened in 2010. A blowout occurred during drilling operations, leading to explosions, fire, loss of life, and one of the largest marine oil spills in history. This disaster changed the way offshore drilling safety was viewed. It exposed the terrifying complexity of deepwater engineering. When something goes wrong far below the ocean surface, human control becomes limited, slow, and extremely expensive. One of the most important defensive devices in offshore drilling is the blowout preventer. It is supposed to seal the well in an emergency, but when the system does not stop the flow, the disaster becomes extremely difficult to control. Deepwater engineering does not forgive weak assumptions. At that depth, every failure becomes harder to see, harder to reach, and harder to fix. After Hurricane Katrina, New Orleans needed more than repairs. It needed a new line of defense. East of New Orleans, a massive concrete wall stretches across the water like a fortress. It cuts across marsh, channels, and open surge pathways. Gates allow vessels to pass during normal conditions, but when danger arrives, the system can close and stand between the city and the sea. It has been called the Great Wall of Louisiana, and the name fits. The lake-borne surge barrier was designed to protect some of New Orleans' most vulnerable areas from storm surge coming from the Gulf of Mexico. It blocks water from taking a shortcut into the heart of the city. The barrier is roughly 1.8 miles long and about 8 meters high. It represents a major shift in flood protection. Instead of waiting for the storm surge to reach the city, engineers built a defense farther out. The wall is built from circular reinforced concrete piles driven deep into the ground. Some piles reach around 30 meters into foundations of rock and sand, while supporting batter piles can reach nearly 60 meters deep. This is not just a wall sitting on the surface. It is a rooted structure designed to resist enormous lateral force from water. For New Orleans, this barrier is not abstract infrastructure. It is a defense for neighborhoods, families, hospitals, roads, and emergency systems. It exists because a city learned what happens when flood defenses are overwhelmed. The Lake Borgne surge barrier shows the other side of engineering disaster, not failure. Memory turned into design. A dam is supposed to control water, but when a dam system fails, the water becomes a moving wall of destruction. Imagine days of extreme rain falling over a river basin. Reservoirs fill, spillways struggle. Dam operators face impossible pressure as water levels rise. Then the structure gives way. A massive flood rushes downstream. Villages, fields, roads, and homes are swallowed in the dark. The Banqiao Dam failure occurred in China in 1975 during catastrophic rainfall from Typhoon Nina. The disaster involved dam failure and massive downstream flooding, with terrible loss of life and destruction. This became one of the most serious warnings in dam engineering. It showed that flood control systems must be designed not only for normal extreme events, but for rare events that push the system beyond expectation. The terrifying lesson is cascading failure. One dam failing can put pressure on others. Roads, communication systems, evacuation routes, and local decision-making can collapse at the same time. Engineering disasters often become deadly, not because one thing fails, but because many systems fail together. The human impact was enormous. Communities downstream had little time to escape. The disaster pushed engineers and planners to think more seriously about emergency communication. The disaster pushed engineers to improve spillway capacity, dam monitoring, and worst-case flood modeling. A dam can protect millions, but if it fails, it can also multiply danger. But while Banqiao was a flood disaster, the next case combines earthquake, tsunami, nuclear power, and the terrifying limits of backup systems. From failed dams in China, we move to Japan, where the ocean itself overwhelmed layers of engineered defense. Fukushima was not caused by one failure. It was caused by a chain of failures arriving faster than the defenses could respond. On Japan's coast, a nuclear power station stands near the Pacific Ocean. Then the ground shakes. The earthquake is massive. The reactors shut down automatically. Backup systems begin their work. Then the tsunami arrives. A wall of water crashes into the site, flooding critical systems and turning a controlled shutdown into a nuclear crisis. The Fukushima Daiichi disaster happened in 2011 after a powerful earthquake and tsunami struck Japan. The reactors initially shut down, but the tsunami disabled backup power systems needed to keep cooling the reactor cores. Nuclear power plants depend on cooling even after shutdown. Without stable cooling, heat continues to build. That is what made Fukushima so dangerous. The disaster revealed a terrifying weakness. Backup systems can exist and still fail if they are not protected from the right threat. The problem was not simply that engineers had no emergency plan. The problem was that the tsunami overwhelmed key parts of that plan. Defense must be designed against reality, not just against what seems likely. Fukushima displaced communities, triggered global debate about nuclear safety, and forced countries to review nuclear plant defenses against floods, earthquakes, power loss, and extreme natural events. It showed that modern engineering must think in chains. What happens if the first defense fails? What happens if the backup fails? What happens if the environment destroys the backup to the backup? Chernobyl did not just destroy a reactor, it changed how the world imagined invisible danger. In the darkness of April 1986, a nuclear power plant in Soviet Ukraine runs a safety test. Inside reactor number 4, power conditions become unstable. Operators struggle with a machine they do not fully control. Then the reactor explodes. The roof is torn open. Radioactive material rises into the night sky. A city nearby sleeps under an invisible cloud. The Chernobyl disaster was one of the worst nuclear accidents in history. It involved reactor design weaknesses, operational errors, and a catastrophic explosion that released radioactive contamination across large areas. Unlike a fire or flood, radiation cannot be seen, smelled, or outrun in the usual way. That is what made Chernobyl uniquely terrifying. The danger was silent, invisible, long-lasting. The disaster led to the evacuation of Pripyat, a city built for plant workers and their families. Streets, schools, apartments, amusement rides, and personal belongings were abandoned. The city became a frozen image of technological confidence turned into ghostly silence. Firefighters, plant workers, engineers, soldiers, miners, doctors, and civilians were pulled into the crisis. Some responders faced extreme exposure. Chernobyl changed nuclear safety culture, reactor oversight, emergency planning, and public trust. It became a warning that complex systems can fail in ways that exceed the imagination. Number 1 is the Space Shuttle Columbia disaster, a tragedy where a small piece of insulation foam struck the shuttle during launch and created damage that would later destroy the spacecraft during re-entry. The countdown reaches 0, 3, 2, 1. Booster ignition, liftoff. Space Shuttle Columbia rises on a tower of fire, carrying national and international research experiments into orbit. The 2 solid rocket boosters burn white-hot on either side. The huge orange external tank feeds liquid oxygen and liquid hydrogen into the engines. Everything looks powerful, controlled, precise. But just over a minute after launch, something breaks free. A piece of foam insulation separates from the external tank's bipod ramp and strikes the left wing of the shuttle. To anyone watching, it looks small. In spaceflight, small does not mean safe. That damage did not destroy Columbia immediately. The shuttle reached orbit. The crew carried out the mission. For days, Columbia moved through space while the fatal wound remained hidden in the wing. Then came re-entry. As Columbia returned to Earth, superheated plasma entered through the damaged area. It penetrated the wing and began melting the aluminum structure from the inside. Sensors began failing. The vehicle became harder to control. Then Columbia broke apart. 7 astronauts were lost. Columbia changed the way NASA and the engineering world viewed risk, culture, and assumptions. The tragedy showed that repeated small problems can become accepted simply because they did not destroy the system before. That is one of the most dangerous phrases in engineering. It happened before, and nothing bad happened. This is how risk becomes normalized. Engineering is one of humanity's greatest powers. It lets us cross oceans, hold back storm surge, drill beneath the sea, split atoms, fly into space, and build tunnels underwater. But every case in this video reminds us of the same uncomfortable truth. The world does not forgive false confidence. A bridge can move until it tears apart. A dam can stand while the mountain destroys everything below. A backup system can exist and still fail. A small piece of foam can wound a spacecraft before anyone realizes the mission is already doomed. Which engineering disaster or defense shocked you the most? Let us know in the comments. And subscribe for more documentary rankings about the structures, failures, mysteries, and technologies that changed the world. In the next video, we'll explore the most dangerous mega projects ever built and why some of them still make engineers nervous today.